All right, I'm Tim Hopper. I'm a data scientist at Cylance. I assume most of you have at least heard of Cylance. We are a next generation antivirus, anti-malware product. Unfortunately, after I submitted to apply to speak here, this is the first security conference I'm speaking at. Actually, the first security conference I've been at. Thank you. I applied and I was like, oh, they probably won't be interested. So I bought tickets to the Mandolin Orange concert in Raleigh tonight. So I'm going to have to jet pretty soon after I talk. But if you want to get a hold of me, I'm happy for you to. I'll stay around for maybe an hour or so, but I'm going to have to go pretty quick. So my background is in math and operations research, which is kind of applied math. Not in cybersecurity so much. I did a minor in computer science in college, but I'm relatively new to cybersecurity in my life, but I've been doing it for, I guess, a little over 3 years now in the data science space. I came into cybersecurity through data science and machine learning type applications. I've worked at Cadium and Distill Networks after that, which is a malicious web bot mitigation company. And then I'm now at Cylance. Love Western North Carolina. Grew up visiting my grandparents here and dream of moving here. One day I'm in Raleigh. I work remotely for Cylance. And I have pictures of the mountains if you'd like to see that. So as I start, there's a distinction that I think is mostly useless here, which is machine learning versus artificial intelligence. In the last couple of years, artificial intelligence has had a resurgence as a term, largely through marketing departments. There's really no significant distinction to be made in talking about applying artificial intelligence versus machine learning. So my talk is challenges of applying machine learning to cybersecurity. You could replace that with artificial intelligence. And it would be exactly the same. Except if you use the term artificial intelligence, people might give you more money, so it's less challenging. But we see these articles coming around, and as I was looking for articles on kind of the hype of AI or machine learning and cybersecurity, there are a lot of articles you see also that are, I think, more reasonable approaches. But these hype articles, executives love to post on LinkedIn and say things like, the scalability and automation capability of machine learning can efficiently analyze large pools of data, correlate simultaneous events, and learn to separate atypical from typical behaviors, thus enabling it to detect potential threats even at an advanced level. And the title there being AI is the future of cybersecurity. And certainly there are a lot of great and valuable applications of machine learning to cybersecurity, but it's not simply just a magic bullet. I mean, this is actually a great follow-up to Dan's talk just now in thinking about automating threat intelligence. And someone could come along and say, well, you don't even need to do all this automation effort. You just need to do machine learning. You just need to do artificial intelligence to your threat intelligence work. You don't have to do all this automation, but manual automation. That's too much. And the reality is that's just the manual effort, the human effort isn't just going away overnight. And applying machine learning effectively is an extraordinarily challenging and thus very expensive thing to do. To try to give a little bit of technical context, I'm not going to go deep into what is machine learning here, but in this talk, I'm largely going to be focused on this concept called supervised learning, which probably many of you have heard that term. Machine learning can roughly be divided into supervised and unsupervised learning methods. And I'm focusing here on supervised learning methods because if supervised learning methods are hard to apply to cybersecurity, unsupervised methods are even harder. So the things that I'm suggesting would apply even for unsupervised methods. But roughly, supervised learning is methods for algorithmically learning patterns from data, terrible grammar here, and making predictions on unlabeled data. So you're trying to learn patterns from data where you have labels of something you're trying to predict that you can then apply the patterns you've learned to make predictions on data that doesn't have labels. So you could think in my previous company in malicious web bot detection, we have essentially enriched Nginx logs coming in before customers making HTTP requests. We get to see this HTTP request, and we want to make some prediction: is the user or system behind that request malicious or not? So you might go add a bunch of labels, manually label data, and learn patterns that you can predict in the future. Or in the anti-malware case, you can collect a bunch of binary files, label them as malicious or not, and then you teach your machine learning model, which is just some sort of mathematical formulation, to detect patterns in those files that correlate to malicious or not, and then you can make predictions in the future. So I'm going to use the term model pretty liberally. It can mean a number of things, but it's really just a function that we can train on some data to make predictions about something. And training means finding parameters for that function to make specific predictions for your example. So you can think of the model in the general class that has all these free parameters that you can fit, and then you are automatically learning or mathematically updating your parameters based on your data to make predictions in the future. So that's maybe a 3-minute introduction to machine learning, just to, if you don't have context, to give you a little more context for the terminology and the rest of the talk. So these are some applications I could think of machine learning in the cybersecurity space. Bot detection, which I was describing, Distill Network provides. I mean, this is a huge space of companies trying to stop malicious actors from stealing their data or DDoSing or doing account fraud, all kinds of things. It's a big space. It's almost impossible to strictly do manually. If for no other reason it happens in real time, you have to be able to respond to your HTTP request instantly. Intrusion detection, biometric authentication, obviously a huge area these days. Malware detection, like Cylance and many others are providing these days using machine learning. Automated penetration testing, and of course, one of the most famous examples, and really one of the most successful examples here, is spam detection. I mean, we all remember our email 15 years ago where we just got tons of spam into our inbox. And now if you use a major email provider, I mean, you almost never see spam anymore. Those are our machine learning models, or probably more realistically, a whole combination of models and probably even some human rules and things. But spam detection is an incredibly effective system. And I think there are probably some reasons actually why about the particular problem that make it easier than others that make it so successful. So if you've done any study at all, even casually into machine learning, you've probably come across one of the most famous sort of toy data sets, and that's the Fisher's iris data. So Fisher was a geneticist 100 years ago or so, and he took 150 measurements from 3 different types of irises. So he measures 4 different parts of the iris, which were the numbers on the chart there, and then there's also the name of the varieties of irises, which are pictured on the right. So a classic example of doing machine learning, or even if you took statistics classes before machine learning became all the rage, you can do this with quote, statistical methods, which are the distinctions there are pretty blurry also. But the question becomes, can you train a mathematical model to receive these measurements as an input and output the type of iris as the prediction? And the data on the left, this is four-dimensional data, so the charts on the left are an attempt to visualize the 4 dimensions in a two-dimensional sphere by just looking at pairs of dimensions together. And so you can see in each of the dimensions, the data is somewhat separated. The colors are somewhat separated from one another. And so you could, even just with a pencil, go and draw a line that says, well, I think this line roughly divides this data. And then machine learning is essentially teaching a computer to draw some sort of optimal line in the higher dimensional space. So this is a really common example. It's very popular. People say, oh, here's how machine learning works. And you can go, pip install scikit-learn with Python, and you could train a whole bunch of different types of machine learning models on this, measure your accuracy, and say, okay, great, here's a machine learning model. I can make predictions and do all these things. But the reality is, even though conceptually there's a lot of overlap between this problem and cybersecurity problems, where you are really just thinking of whatever data you're dealing with, whether it be your web logs or your binary files or something, you're just thinking of a mathematical representation, a vector space representation, essentially. You're transforming your data into numbers like these and saying, can I learn patterns in those numbers? So there is that similarity, and yet the realities of a, quote, toy problem like this and using machine learning effectively in a real-world production environment are just worlds apart in terms of what it actually looks like. And my desire here is not to be like a gatekeeper for machine learning and try to scare people off or discourage you from going out and just take an introductory Coursera class and look at problems like these. Really, if anything, my desire is to encourage you to be a skeptic as you hear companies marketing spiels about their machine learning and artificial intelligence, and hopefully ask questions better, and also just be able to evaluate the claims that they're making. And to know that Cylance has solved all these problems and our product is perfect. If anybody's listening. Several aspects of this problem that distinguish it from many real-world problems, and then more specifically from cybersecurity problems. One is we're dealing with a static data set here. So if you're doing machine learning models on this, you have 150 data points. You could go collect more data if you wanted, but if you're simply operating on the toy example, it's just easier to deal with data that you know and that you know isn't growing. Similarly, it's very low dimensional problem. So we have our 4 dimensions of data, and it's just easier for us as humans to conceptualize. It's easier for models to find patterns in. It turns out there are a lot of things about low dimensional data that the analogies don't extend into higher dimensions, and that's a whole nother talk on itself. But we can conceive things about 2, 3, 4 dimensions that if we think about hundreds of dimensions, the things we might assume don't apply. The data is mostly separable, and by separable we mean if you as I mentioned before, if you look at those graphs, you could draw a line between the colors and do that pretty effectively. One of the challenges of doing machine learning on more complex problems is defining your features, which is your numerical representation of your data, in a way that makes it separable. The data is pretty interpretable. I mean, Fisher is, these are measurements straight from your flowers. Interpretable data makes it easier to interpret how your models are operating and understand how they're operating and understand when they're failing. If you wanted to get more labels to your data, if you only have 150 data points here, say you needed 1,000 data points, you could pretty easily, if you can find enough irises, you could pretty easily go out and collect more measurements. And similarly, if you knew, I actually don't know how Fisher's measurements work, but if you understood how they worked, you could train someone else to go make those same measurements pretty effortlessly. That turns out to certainly not be the case in cybersecurity. And finally, this problem is somewhat stationary, which is a technical term in the statistics world. But when we think about stationary, I mean, it's more like how we just use it colloquially. It's that the data isn't changing. If we added more flowers, or we had to do this in real time, so say we're a iris processing factory and we had a machine that could take these measurements and we wanted to know what types of irises they were, it's reasonable to expect that the measurements are not going to be coming from a different distribution of data over time. I mean, maybe the flowers regionally vary or even seasonally vary, but we would hopefully expect that an iris now and an iris a few years from now of the same variety is going to have measurements that are from the same type of distribution. So all that to say, cybersecurity is not a bed of irises. The iris problem as a toy example is helpful in understanding some aspects of what machine learning is, and yet it really covers up. That's not fair, really. It just is not as complex as the reality of machine learning and real world problems. I think covers up is unfair because it's not. Fisher wasn't making any claims that his data was applicable for those trying to apply machine learning to cybersecurity 100 years ago. You might have heard about deep learning. One of the popular things today, you might come along and say, well, yeah, this was true before 2009, but now we have convolutional neural networks, or now we have recurrent neural networks, so it's actually easy now. That's just patently false. Deep learning is really extraordinary at solving some problems very well, and yet most of the caveats I'm going to give here still completely apply. So don't let people trick you into that. And for the most part, deep learning is not categorically different from the things that people were doing prior to it. It has some, it does have some advancements, but it's not just completely different. So 9 challenges to applying machine learning to cybersecurity in the next 25 minutes. One is defining the problem. So we could think about all kinds of definitions to cybersecurity. Here's just an arbitrary one. Cybersecurity entails the safeguarding of computer networks and information they contain from penetration and from malicious damage or disruption. In Dan's talk this morning, he was saying one of the challenges that you need to accomplish for effective threat intelligence is to really understand what problem it is that you're trying to solve. And in my relatively limited experience with cybersecurity coming into this world in the last few years, you realize that it's easy to say terms like malicious or damage or disruption, and yet to concretely define what that means in a way that you could teach a computer to recognize those things can be significantly more challenging. It's not necessarily black or white how you define those things. Charles Kettering, who is head of research at General Motors in the very early days, and is famous for a number of things in that space, has a quote: "A problem well stated is half solved," and that could not be more true in applying machine learning to your cybersecurity problems. That just getting to where we know what problem it is we're trying to solve is at least half of the work in actually solving the problem. So in the malicious web bot space, there's two immediate questions you can ask. You have traffic coming to your website and you want to block malicious bots. The first question you have to ask is, what is a bot? I mean, a bot could does it strictly mean a computer operating independent of a human operator? All kinds of difficulties there. And if you define it, can you detect it is another question. And then secondly, what is malicious? What's a bot with malicious intent versus a bot without malicious intent? In many ways, that depends on who the end user is as to how you're going to define that. Also, you could think of a sense in something might have both malicious purpose or intent and not. I mean, you can get into ethical questions there. There are just all kinds of questions that have to be answered before you're deciding how to do that. In the malware space, what is malicious software? A temptation for a company blocking malware is to prevent any system from running auto IT, because you can do all these dangerous things with auto IT, and yet many people use it as an important part of their toolkit in running their companies. It's an example of software that has both good and bad uses. And can I necessarily know? I want to try to come up with a definition of malicious software. Just because I define it, can I actually know it when I see the software? How do I know that I can know that? And then similarly, does the definition of malicious stay constant over time? I mean, a somewhat simple example is you could think of a piece of malware from 20 years ago or something that can no longer run on a system, or maybe it was malware that operated on a system that we know has been patched to where the malware can no longer execute the malicious functions. If it can't do any damage, do we still consider it malicious? And you could think that can get more complex examples of that. But all that to say is nailing down what you actually mean by the problem is very challenging. And going to a data science team, potentially speaking from experience here, going to a data science team who aren't domain experts in your particular realm of cybersecurity and telling them, oh, go block this malicious thing, go prevent this malicious thing, and then just kind of hemming and hawing when they're asking you what you mean by malicious, what you mean by damaging, that just doesn't work. I mean, there's no magic thing in data science that knows what malicious means. Similar to that, supervised learning is effectively pattern matching. I presented this talk to my colleagues this week, and my one colleague's complaint was that there were no dog GIFs. So this is the best I could do that was somewhat relevant. But anyway, doing machine learning requires a sufficiently large amount of accurately coded examples. So you're training a computer to recognize patterns. It has to have some kind of ground truth to recognize those patterns from. And in most cases, it needs ground truth from both what we call positive and negative examples. So if you're talking about malicious versus not, you need a good number of examples of malicious things and a good number of examples of benign things. And this is one of the biggest challenges for anyone applying machine learning. And I saw a relevant tweet last night, quote, from every CEO ever, I thought AI meant we didn't have to label data anymore. And that's just not the case. Having data, good labeled data, is still essential for doing machine learning. And this is one of the areas that in the space of image recognition, deep learning has really made changes because it has essentially reduced the need. It's allowed the models to learn more things from unlabeled data and then learn faster when you then have labeled data. But that's deceived people into thinking that we just don't need labeled data anymore. So in the case of Cylance or anyone doing machine learning in the anti-malware space, we have teams of human experts who are executing files in sandboxes, who are looking at decompiling files, doing all this research into whether or not things are malicious. We're collecting examples of non-malicious software to just store as examples so that we can learn. We need to be able to learn the patterns both in malware and in non-malicious software. This is a huge challenge. Is very expensive, and just is absolutely essential. This, going back to the iris example, you're talking about how irises, you could really train someone to label iris data by taking the measurements. It just requires a more advanced skill set to train someone to distinguish between examples in the security space. And more advanced skill set means more expensive. This is definitely one of the hardest problems in all of my examples. Challenge 3: what's the cost of predicting incorrectly? So machine learning models are never going to be completely right all the time. If you want to never incorrectly say that something is malicious with your machine learning model, it's never going to be able to say anything at all. If you're making predictions, it's going to be wrong at times. So from the business perspective, you need to be able to quantify, or at least attempt to quantify, what are the implications of a machine learning model being wrong, particularly if it's making automated decisions. So again, using examples from spaces I've worked in the malicious web bot space, your machine learning model's wrong. Suddenly on Black Friday, it starts blocking people from accessing your website who are trying to buy items that you have on sale, and you're immediately losing revenue because you're blocking people from your website. Similarly, in the bot blocking space, if you block humans incorrectly, they're going to get mad at you and they might not come back again. Or you might fail to block there's an advanced botnet, you fail to block it, it DDoSes your site. That can be very costly. And I think in those cases, the loss of revenue is easier to quantify. Sometimes I think the cost of being attacked might be harder to quantify. In the malware space, obviously if we fail to block malware, our customers get ransomware on their computers. They blame us for not blocking it. Very costly to them, very bad for our reputation. We block things incorrectly, and this is actually a important nuance. Is if we block something incorrectly, we might annoy people a little bit, but in the malware space, you can then go in and whitelist something. It doesn't have as detrimental effects as maybe blocking someone from buying something on Black Friday. And the nuance there is that there can be a huge imbalance for a malware provider. There's a big imbalance between blocking something incorrectly that's not malicious, or failing to block something malicious. So failing to block something malicious could have these huge detrimental costs. Blocking something that's not malicious is mostly just annoying, unless you do it too much and it really damages your reputation. And why that nuance is important is as you're training machine learning models, so as you're fitting your model to your data, most machine learning models, if you just use the default settings, are assuming that those two costs are exactly equal, that the cost of a misclassification, a false positive or false negative, are the terms used, are equal in cost. But the reality is probably in most spaces that's not true. And then beyond that, the challenge is how do you actually quantify those costs or measure them to evaluate your models and evaluate whether or not they can be used in production. I'll try to refrain from saying at each point that this is one of the hardest problems, because these are all real challenging problems. Number 4, model predictions decay over time. This is the technical term is model drift. That machine learning models being used in largely human systems and maybe other things tend to get worse over time unless you're continually updating them. So one of the advantages of Cylance as a product, or potentially other machine learning driven antivirus, anti-malware tools, is we can actually predict, we can block malware in the future from models that we train now, because we're not looking just at databases of hashes, we're looking at patterns inside malware. So we can stop things in the future without having seen them before. That's one of our huge selling points. And yet, if we just stopped now and said, well, we can predict things in the future, we can block malware that has not even been written yet, just stop now and rest on our laurels and drink a lot of beer, our models are just going to get worse and worse. So there could be all kinds of examples for that you could think of, or reasons for that you could think of. One being, the malware authors are going to learn how to work around our tools, or simply that the systems are changing, the operating systems are changing and updating. So maybe we're looking at patterns that just aren't applicable in the future. Yeah, so there could be other reasons there as well. But if we just stop and use these trained models, they're going to get worse and worse. So once you start doing this, you have to stay on top of it. And this is not just in the cybersecurity space, but in any type of machine learning models. Dynamically updated models are rarely used. If someone tells you that their machine learning model is learning all the time as new data comes in, they're probably actually lying to you. That's what every marketing team wants to say. And there are cases in which you can do that. But the challenges of doing that are typically insurmountable for a number of reasons. Sometimes just the structure of the machine learning models aren't conducive to what's called online learning, which is that they're learning from data as it comes in. There's way too much risk in the models being gamed. If you're doing that, you could, you have a model that's recognizing malware, and someone does something to just throw tons of examples at it that are forcing it to go off course. And just a number of other reasons, but this is a really, really, really hard thing to do. Everyone wants you to think that they're doing this, but it's virtually impossible in many applications. Exception being, sometimes you can make like some local adjustments. Something like you think of Face ID on an iPhone or something. They have a machine learning model that's making these local adjustments to adapt to your face. That is actually a real-time example, but it's there's still like underlying it's making changes to small parts of the model where they're underlying things that are having to be static and then updated in a more controlled environment. Adversarial actors have an incentive to bypass your models. So this, someone made this video when I was working in the bot mitigation space. And right, so it's this robot arm clicking the "I am not a robot" box. And I mean, it's just, you know, it's silly, but there's so much reality behind this as to what is going on, and that, you know, so the computer has cookies that Google thinks is good, and so there's, you know, it's not quite as simple as this, but the reality is that if you are trying to stop someone from doing something that they have an incentive to do, they're going to try to find ways around your model. And this is something that we spend a lot of time on in the malware space, is making our models so that you can't just you know, add a bunch of junk code. You have some malware and then you just add a bunch of junk code that doesn't do anything, or maybe doesn't even execute, and all of a sudden your PE file looks different, and so then the model fails to classify it as malicious, or things like that. We spend a lot of time hardening our models to prevent this. But malicious actors have a incentive, for whatever reason, financial or otherwise, to get around your security products. They're gonna continue to try to find ways around it. And there's a subtler thing here, which is that repeated access to model predictions allows adaptive behavior. So if you have your machine learning model accessible in some sort of Oracle form, which unfortunately an antivirus or anti-malware tool is, either in simplistic ways, or actually there are more kind of advanced mathematical ways, people can yeah, that's a great way of putting it. They can model your model, and they can intelligently decide how they throw data at your model to see what it predicts, to then try to find out ways to work around it. This is basically unavoidable in the malware space, but in other spaces, you might be able to limit access that someone has to your model, but you're in some sense giving away data as you make your predictions visible. Challenge 6, feedback loops. Blocking malicious actors changes the nature of your data. So the bot mitigation problem is a really good example of this. So you have a bunch of weblog data that you manually somehow magically classify as malicious or not, and then you want to train a model to recognize future logs as malicious actors or not. So then you put your model into production, start running it, and then you start blocking all this malicious traffic, which is changing your log data. So you have less malicious traffic because you're, and a reason for that is, you know, in weblog data, a malicious actor doesn't just have one log line, they have hundreds or thousands or millions of log lines. And if you're able to effectively stop them, they might just have one or two. You see them a couple times, you block them out of your their HTTP requests, and they're gone from your data. Then your model drifts, as we talked about. Your model decays over time in quality. And so you need to go retrain your model. And you don't want to retrain it on old data. You want to train it on new data. But your new data is biased against the malicious actors because you're removing them from your data. So you're then training a model on data that's biased from the naturally occurring data that you would have apart from your mitigation strategies. So this creates a feedback loop that, if you don't take into account, you retrain your model and suddenly you get worse predictions, and you have to explain why. There's a really amazing paper from a Google researchers called machine learning the high-interest credit card of technical debt. Great title, and it's just a great paper. If you're interested in a production machine learning system, or if you're doing it already and you haven't read this paper, you really should go read it. It's very approachable. It's not highly technical, but they talk about this feedback loop problem and then just a number of the other challenges of running a production machine learning system that may scare you off from really doing that. Challenge 7, data access. I'm going to speed up a little bit so I have some time for questions. By the nature of security problems, we're dealing with data that's restricted. Are you, as the researcher, going to be able to get access to your data to learn patterns from it so that you can make predictions of the future, from the future? Similarly, can you get access both to a malicious and benign class data? In some examples, someone's happy to give you their examples of malicious data, but they can't share with you any benign data because it's like their private business files or whatever. Somewhat unexcitingly, GDPR is changing this also in that if you have customers in Europe, they might be legally prohibited from allowing you to take their data into the US to train a machine learning model on it and then send the machine learning model back to Europe. We're hiring malware analysts in Ireland specifically to look at data that we're not able to bring to the US. It's just the reality of the way it is, but it's actually changing how people are going to do business. Are you going to be able to get access to the data that you need? Challenge 8, model interpretability. Many classes of machine learning models are inherently difficult to explain. And by that we mean the predictions that they make. If someone comes and says to you, well, why did it make that prediction on this piece of data? Even defining what explainability means is a challenging thing on its own. But assuming you have some definition, some machine learning models do such convoluted things with your data that it's very difficult to give any explanation other than just like a literal showing what it did, which is like, oh, well, we just modified it or multiplied these things by these decimals and did these mathematical operations, and then we got a result, which is meaningless to anyone who really is trying to understand why that happened. But if you provide some sort of security product that your CEO dog foods, something's going to happen where your CEO sees something get blocked or something not get blocked or something along those lines that he doesn't expect or she doesn't expect, and they're going to come to your data science team on Monday morning and tell me, why did this thing happen? And you get to be Mary Poppins, the neural network, and just walk away and say, I can't explain this. But analyst teams, your customer success teams, your customers, potentially regulators in some spaces, are going to want to know answers to these questions. And if you haven't put forethought into this, it's going to be very hard for you to provide those answers. Yeah, this is a huge question in machine learning in general that people are wrestling with, but it comes up a lot in my work. Yeah. There's more to be said there, but I'll save that for another talk too. Finally, this is my worst title challenge, non-Pareto model transitions. And this is probably also one of the harder things to conceptually understand if you haven't worked with machine learning. But machine learning models, as you update them, which we call retraining, they can introduce regressions in the classifications. And this is regressions not in the statistical sense, but more in like the software testing sense, where your model that once made a correct prediction, if you update it, in some examples, might suddenly start making incorrect predictions. And even worse, for some types of machine learning models, because most machine learning these days is like a probabilistic type methods. They're depending on these statistical algorithms for finding the parameters for training them. You could have a machine learning model that you train the exact same model on the exact same data, and you, in some cases, even if it's a very good model, in some cases you could be getting different predictions just because of the nature of the probabilities. So this can introduce security holes. We deal with this in the malware space. You want to retrain your model, and you've always, your model's always blocked some known malware thing, and then you train your model, and for whatever reason, kind of going back to explainability, it might be hard to explain. It suddenly stops blocking the model because we're dealing with probabilities, or it suddenly stops blocking the malware. Or maybe, you release your new model and you're blocking malware, and all of a sudden your new model is blocking Microsoft Word on all your customers' computers. This is not like it's universally worse. It's not like it's just getting everything wrong. The reason for choosing non-Pareto as the term is it's just that it's probably not going to be better in every possible instance. It's going to be better in a lot of instances, but in some instances you're going to have these regressions where your model suddenly starts being incorrect. There are ways that you can then deal with this, but however that is, the reality is that you just have to deal with it. You can't just let this happen. And in many applications, probably there's some when you can get away with that. So, in conclusion, 9 ways that machine learning is challenging to apply to cybersecurity problems. 1, just defining the problem. 2, getting labels on your data, having your data being labeled as malicious or not, or whatever your taxonomy is. 3, what's the cost of being wrong? Can you even quantify it? And if you can quantify it, how expensive is it going to be to quantify? Then can you fit it into your models once you've done that? 4, models decay over time. In the real world, you have to deal with models getting worse as the world around them changes. 5, adversarial actors have an incentive to work around your models. 6, bias feedback loops are going to change your retraining, your updating of your models unless you control for the feedback that you're getting. Recognizing that as you act on your data, you're changing the nature of the data. 7, can you even get access to the data that you need? Can you get it out of Europe? Will your customers allow you to have it? Do you have to work on their system? Can you put it in AWS? All these questions. 8, model interpretability. Once you get a machine learning model and it starts making predictions, are you going to be able to tell why those predictions were made and what they mean? And 9, model instability. Your models, as they transition, might suddenly make bad predictions that are going to cause you trouble. I'm happy to take questions. I don't know on the time.
We got maybe 1 or 2 minutes.
All right.
In terms of the decay and instability, do you think there's any potential using machine learning for like harvesting defined cool stuff and then shuttling what it learned over into, say, a new product or a classic expert system or something like that? The good things you learn can persist and won't degrade in the model.
Yeah, so the question is, can you use machine learning to detect interesting things and then maybe somewhat manually put those into an expert system or something like that? Yeah, so there's a lot of possibility for that depending on the application. You could certainly do that, like a manual review. You train your machine learning model and then it's detecting things that you're manually evaluating. That completely is application dependent, but there's certainly a lot of opportunity in many problem spaces for kind of the human machine learning model interaction to yeah, I mean, it's basically like Google, right? Google is a machine learning product that's just ordering your search. It's doing the search and then ordering the search results, right? So it's putting the things at the top that you think might be interesting. There are a lot of analogies to using analysts and products, machine learning products together. All right, we're going to wrap it up there. I'll be around for a little while. If people have more questions, I'm happy to talk. Thank you.
All right. Again.